Hello and welcome to Otten Math. In this edition of Otten Math, we're going to talk about recursive rules. If you recall, we talked about explicit rules for arithmetic and geometric sequences, and today we're going to talk about recursive rules. All right, so as a refresher, explicit rule talks about providing a value for any term in the sequence based on a formula. So all you need is, for arithmetic sequences, is you need the first term and then the common difference. And for a geometric sequence, you need the first term and a common ratio. And with those two pieces, you'll be able to figure out the nth term in any geometric or arithmetic sequence. So for an arithmetic sequence, as a refresher, a sub n is equal to the first term plus n minus 1 times the common difference. And for a geometric sequence, a sub n, the nth term, is equal to a sub 1 times the common ratio to the n minus 1. All right, so let's talk about recursive rules. So with recursive rules, you need the prior term and the common difference and the prior term and the common ratio in order to find the subsequent term. So a recursive rule defines the value of a term by relating it to a preceding term. And so in my opinion, the recursive rules are a little less handy in finding the nth term because you need that preceding term in order to find that subsequent term. So if you want the sixth term, you need the fifth term. If you want the eighth term, you need the seventh term, and so on. All right, so again, the rule for the arithmetic and geometric sequences for explicit rules, and then the rule for the recursive rules for arithmetic and geometric sequences. All right, so let's also talk in the context of discussing or finding the recursive rules and values for the nth term using recursive rules. We need to also talk about iterative functions. And iterative functions are functions in which we take some input into a function, then we receive an output from the function, then we take that output and then subsequently put it into the input of the same function and so on until we're done with either a finite sequence or iterative functions and we come up with a final answer. So as an example, x sub 0 is equal to 2. My function f of x is equal to negative 3x plus 1. I'm going to take my value x sub 0, which is equal to 2, substitute that in to the function. So I have negative 3 times 2, which is negative 6 plus 1, and I end up with negative 5. So x sub 1 ends up being equal to negative 5. Then I'm going to take the value for x sub 1. I'm going to substitute it into the function to find x sub 2. Negative 5 times negative 3 is 15. 15 plus 1 is 16. X sub 2 is 16. And I'm going to take x sub 2, substitute it in for x for f of x to find x sub 3. F of x sub 2, 16 times negative 3 is negative 48 plus 1, negative 47. So that's an iterative function. So I'm taking the output, becomes the input into the function. I take the subsequent output, it becomes the input to the subsequent function. All right, so I want you to take a look at this sequence. A sub 0 is 7, a sub n is equal to the recursive rule. A sub n is equal to a sub n minus 1 minus 3. And then you're going to work through all these to find out what a sub 5 is. I'm going to pause here. All right, so a sub 2 is equal to 4 minus 3, it's 1. A sub 3 is equal to 1 minus 3, negative 2. A sub 4 is equal to negative 2 minus 3, negative 5. And a sub 5 is equal to negative 5 minus 3, negative 8. All right, so I want you to find a sub 5. A sub 1 is 2. And the rule is a sub n minus 1 squared minus 5. So this is neither geometric nor arithmetic. All right, so a sub 2 is equal to 2 squared minus 5. 4 minus 5 is minus 1. Minus 1 squared is 1. Minus 5 is equal to negative 4. Negative 4 squared is 16. Minus 5 is equal to 11. 11 squared is 121. Minus 5 is equal to 116. All right, so you can see how the recursive rules model iterative functions. All right, so let's write a rule for the sequence 2, 5, 8, 11, 14. Let's first determine if this is geometric, arithmetic, or neither. And by the way, these rules don't have to be arithmetic or geometric. Right, so we've determined that it's arithmetic common difference of 3. A sub n is equal to a sub n minus 1 plus 3. So that's our rule, and it's arithmetic. All right, so write a recursive rule for the sequence 6, 9, 15, 24, 36, 51, 69. All right, we can see this is neither arithmetic nor geometric, so you're going to have to come up with a rule yourself based on finding the differences between the terms, and then using that to figure out what the rule is for the sequence. So I have difference 3, 6, 9, 15. I can see that the difference is going up in increments of 3, and then I can relate that to the prior term. So every term I go up by a difference of 3. So a sub n is equal to a sub n minus 1 plus n minus 1 times 3, which is okay for my classes to express it that way, but for most other teachers, you want a sub n is equal to a sub n minus 1 plus 3n minus 3 to simplify and distribute the 3. All right, so we're coming on the last portion of the class. Now let's apply what we know to an application. On January 1st, 2006, we have $100 in savings account that earns an interest rate of 1% per year. At the end of every year, you're going to accrue that 1%, and then you're going to add $75 into the account. So I want you to write a recursive rule for the total amount you'll have after n years. And then I want you to use a recursive rule to find the total balance to the nearest penny on January 1st, 2011. All right, so we want to write a recursive rule. So we know that on, and I'm going to do this kind of in reverse order a little bit. I'm going to answer number 1 first. So a sub n is equal to a sub n minus 1 times 1.01. So I'm taking the entire balance or principal and I'm adding 1% of interest. And then at the end, I'm going to add the $75. So $75 is not included initially in the interest accrual that I've had over the course of the year because it wasn't part of the balance during the year. I just put it in at the end of the year. All right, so a sub n minus 1 times 1.01 plus $75. And then we go through that iterative function to find out what the balance is at the nearest penny on January 1st, 2011. So I take a sub n minus 1, 100 times 1.01, 101, plus 75 is equal to 176. 176 times 1.01 plus 75, 252.76. 252.76 times 1.01 plus 75, 330.29. And then 330.29 times 1.01 plus $75, 408.59. And then 111, 408.59 would be at the beginning of the 2011, but I'll just take this to the end, times 1.01 plus $75 is equal to 487.68, and that answers a different question at the end of 2011. All right, so I want you to find the first 3 iterates of the function for the given value. And that'll be it for this edition of Otten Math. All right, you'll see 8, x sub 0 is 8. 2 times 8, 16 minus 7, 9. 18 minus 7, 11. 22 minus 7 is 15. All right, that's it. Thanks for joining us and talking about recursive rules. Let's talk next time when we talk about finite series for both arithmetic and geometric sequences.